Okay, so yesterday we have discussed regarding transformer efficiency. Okay, how to calculate the transformer efficiency, and we have seen what is the condition for maximum efficiency also, right? And kVA corresponding to maximum efficiency and current, that means the secondary current corresponding to maximum efficiency, that also we have seen by these two equations, right? And the condition for maximum efficiency is core losses should be equals to the copper losses. Okay, right. Core losses are fixed and copper losses occurring at that particular current. When those two are equal, then you are going to have maximum efficiency for the transformer. Right. So that we have already seen. So now we'll see how to calculate the transformer efficiency. That means in the form of a formula. Right. So efficiency at full load. Right. We are talking of calculating the efficiency at full load. Right. So efficiency is basically output by input, or you can call it as 1 minus losses divided by input. Right. How we have got this? Right. Output by input means output can be written as input minus losses divided by input. Okay. Right. So if you divide the input on both sides, so you will get that 1 minus losses divided by input. Right. So formula can be written in this format also, which is given as 1 minus losses occurring at that load. So if it's full load, at full load, what are the losses? That will be divided by the input. Okay, right. So if you want to calculate efficiency at full load, 1 minus PC. PC indicates the core losses in the transformer, which are usually constant from no load to full load. Okay, so PSC. PSC is the full load copper losses. Okay, copper losses or ohmic losses or I square R loss. All three mean the same, right? So that means at rated current, that means at full load current, what are the copper losses? That is denoted as PSC. Okay, and what will be the input at that condition? That means rated volt amperes into the power factor at that condition plus again the losses, right? Because this is the output. Output plus losses is nothing but your entire input, right? So 1 minus losses divided by input, right? So by using this formula also you can calculate the efficiency. That means output by input only we have changed into this format. That's all, right? What will be the efficiency if I want to calculate efficiency at some fraction of the full load? Right, let's say n is considered as a fraction of the rated full load current. You are getting right? So we are trying to calculate efficiency at not full load. Let's say some condition has come to us, right? At that instant, the current flowing in the secondary winding is observed to be n into the rated full load current. That means some fraction of your full load current. That fraction is nothing but n. Okay. In that scenario, how this formula will change? Can you guess? You are understanding my question now? Current is not the full load current flowing in the transformer. Okay, let's say some I2 is flowing. I2 is equals to N into I full load. That means there is a condition, right? I2 is some fraction of your full load current. That fraction is given denoted as N, let's say. In that scenario, if I want to calculate the efficiency of the transformer, how this formula is going to be modified or altered? Can anyone have a guess on this? How it will change? What will be the core losses if current flowing is I2? I2 is equal to N into IFL. What will be the core losses in that condition?
I1 square R.
core losses in the condition when your current is not full load current I2 is some fraction, let's say n is equals to 0.5, let's call it. Okay, so 0.5 of full load current. In that scenario, what will be the core losses in the transformer? You are understanding, right? Okay, core losses depends on current or not. Core losses depends on current or not. PC depends on current or not. It will depend or not.
Sir, it depends.
It depends. Core losses. Is it so?
No, sir.
In equation 1 above, core loss PC is constant and the load voltage is V2. If you see somewhere else also I might have stated. Right. Core losses under normal operating condition, the variation in the mutual flux phi from no load to full load, that means no load to full load current, is only 2 to 3%. Consequently, the core losses can be assumed constant at all loads, that is independent of current. Right. This statement is already told to you. Okay. Right. So now core losses depends on current or not.
It not depend.
It will not depend, na? So core losses are going to remain constant. That means if I want to calculate the efficiency at some other load current, this value PC which you have got, let's say you have got from operating, that means conducting no load test. Okay, so that will be constant. It is not going to vary. Okay, what about PSC? PSC stands for what? It
Copper
represents
loss.
which loss? Copper loss.
Copper loss.
Okay, copper loss depends on current or not?
Yes, sir. It is I square R.
Right. I square R. So copper loss depends on I square, is given as generally given as I square R. So it depends upon the current. Okay. So at full load, if I am saying the copper losses are denoted by PSC at some fraction, let's say N. That means now the current is not IFL, I full load. It is current is N into IFL. Okay. In that scenario, what will be this ohmic losses?
N square IFL square R, sir.
Okay, N square IFL square into R2, whatever it may be, RE2. Okay, right. So IFL square into RE2, I am denoting it as PSC. That's what I told. Na PSC is the full load copper loss. Okay, at rated current. Okay, so that means N square into PSC will be the copper losses at current I2. Okay, that means you have to multiply with N square. Full load copper losses should be multiplied with N square. Okay, that are the losses which are occurring at that current I2. Okay, what about this one? Rated VA into cos of theta 2, that we have told. Na? This is rated output power, correct? Na? Rated voltage, that means rated secondary voltage into rated secondary current. That's what it means, right? So rated volt amperes into cos theta. So this will give you the rated output power in watts, right? This is called as rated output power. If current is only some fraction of, that means n times that of IFL, then how this will be altered? That means what will be this value? You are understanding the question, right? Transformer is rated for 20 kVA, let's say. It's not necessary that always the rated current should flow on the secondary side. Okay, sometimes I can have, I mean, 10 motors connected to the secondary side of the transformer. Okay, motor is one which is consuming power. Okay, after some time 2 motors may be shut down, right? So in that scenario there are only 8 motors running on the transformer. So that means your secondary current is not the rated current, it has come down because the number of motors running on the transformer are reduced. Okay, so that means the load current secondary side is not in your control, it is going to vary based on the instruments connected on the secondary side. Okay, so this is the denominator, rated VA into cos of theta 2 is the rated power output. Okay, if current I2 is N into IFL, in that scenario what will be this value?
It is n times the previous ones.
Right, so it is N times the previous one. Why means in this formula what you are seeing, V into I. So V is the rated voltage, I is the rated full load current. Okay, when I am saying the current on the secondary is some fraction of full load, that means N into IFL. So that means in this scenario A amperes will be N into IFL. Okay, so that means N into rated volt amperes into cos of theta 2. Okay, so that means N term will come, will get multiplied to this. Okay, right, so that's what we have discussed till now. So efficiency at any load, okay, any load current. Okay, so that load current is now N into IFL, that means some fraction of your full load current. In that scenario the above formula what we have seen, efficiency formula, will be changed to this format. Okay, that means efficiency is always output by input, so 1 minus losses divided by input. So losses occurring at this current N into IFL we have to calculate. So this is the core loss and this is the copper loss occurring at N into IFL, right? So that's N square PSC come, and the rated output at this current N into IFL will be N into rated volt amperes into cos of theta 2. Okay, plus same thing, output plus losses, right? So efficiency is 1 minus losses occurring at that specific current divided by output at that specific current. Got it? Is it clear?
Okay.
So why this formula has changed? Okay, right, so this part is already we have already seen. So as before, the maximum efficiency occurs when ohmic losses is equals to the core losses. Core losses are always remaining constant, that is PC, and ohmic losses will be depending on the current. So N square into PSC. Okay, PSC is the full load copper loss and N square we are multiplying. So that means N square PSC is equals to PC. Okay, so that means N is a fraction which is given as root of PC divided by full load copper losses. Okay, kVA corresponding to maximum efficiency we have already seen, which is N into rated kVA of the transformer. Okay, right, so these all things we have already seen, and this is the basic formula we are going to use for calculating the efficiency at different currents. Okay, so we'll try to check one problem based on this. Okay, so it was given like a 10 kVA. 10 kVA is the rated volt amperes output, and 2500 by 250 volts 50 Hz single phase transformer gave the following results. Okay, so that means open circuit test and short circuit test they have done. Okay, right, and they have done at 250 volts, 0.8 amperes and 50 watts is the data you got from open circuit test, and from short circuit test you are getting 60 volts, 4 amperes and 80 watts, right? So calculate the efficiency at 1/4 and half and at full load operating at 0.8 power factor. Okay, and second thing is second part is calculate the load kVA output at which maximum efficiency occurs. and also find the value of maximum efficiency at 0.8 power factor. Right. So how to proceed for this? First of all, we have to check whether open circuit test is done at rated voltage or not. Okay. So usually open circuit test, high voltage winding is open circuited and low voltage rated winding should be applied. Right. So that's why 230 volts is there. That means the open circuit test has been conducted on LV side because 250 volts during this test is equal to the rated voltage on LV side. That means it is done with rated voltage applied on the LV side. Similarly, short circuit test, rated current should flow. Okay. And if you calculate the rated current, short circuit test instruments will be placed on, generally will be placed on HV side or LV side. Short circuit test instruments means meters will be connected in HV side or LV side.
LV.
Which side?
HV side.
HV side. Okay. So short circuit test, usually low voltage winding is short circuited and all the instruments will be placed on the high voltage side. Okay. So high voltage side is 2500 side. So that means you have to calculate what is the rated current on this side. So 10 kVA divided by 2500 will be 4 amperes and your short circuit current is also 4 amperes. So that means your test was carried out at rated current, and at rated current you have got this much reading of your wattmeter. So what this 80 watts indicates? 80 watts indicates what?
Copper loss, sir.
Yeah, full load copper loss, right? So 80 watts indicates full load copper loss. Okay. So now we will try to calculate the efficiency at 1/4 of the full load. So try to do that. To calculate efficiency at 1/4 of full load and 0.8 power factor. How to do? Okay, what is PC value? Now, what is the value of PC? Core losses?
50 watts.
Okay, so core losses are 50 watts. Now you have to find out copper loss at 1/4 of your full load current. So try to calculate that. Copper loss at 1/4 of your full load current. What will be that value? What will be copper loss at 1/4 of full load? What is
15
N here? 15. How you have done?
Sir, I done n square FL square R.
N square into IFL square into R. So what is IFL square into R here? What is
Full
the-
current is 4 amperes, sir.
Okay.
I calculate resistance as V by I, sir. 60 by 4.
Okay, but you don't know IFL square into R straight away from the data given here.
Sir, 50 by 16.
How much?
50 by 16, sir.
50 by 16. Anyone else who have different answer from this?
Sir, 80 by 16.
80 by 16. Okay,
Yes, sir.
right. Anyone has different answer from these three? Okay, so short circuit test data is given here. So short circuit test is conducted at full load current, because if you see the full load 10 kVA divided by 2500 is 4 amperes. So full load current is flowing. In that scenario, they have given your wattmeter reading. So at full load, as we know, short circuit test is done to calculate the copper losses. Okay, and the current is 4 amperes. That means full load copper losses are straight away given as 80 watts from the short circuit test data. Okay, so 80 watts indicates the full load copper losses, which is IFL square into RE2. Okay, right. So IFL square into RE2 is straight away equal to 80 watts. Okay, at 1/4 of the full load, if you want to calculate the copper loss, so 1/4 whole square into 80. So that will be 80 divided by 16. So that will be the copper loss at 1/4 of your full load. Right. So we'll see that efficiency at 1/4, half, and 1 of full load is need to be calculated. Ohmic losses at full load is straight away given from the short circuit test data, which is 80 watts. Core losses, which are constant at any load, are 50 watts. That is coming from open circuit test data. Okay. Now, ohmic loss means copper loss at 1/4 full load is 1/4 whole square into PSC. PSC is 80 watts, right? So it will be 80 divided by 16, which is equals to 5 watts. Okay, right. So what will be the output power at 1/4 of the full load? Output power in watts at 1/4 of full load. As we have already discussed, at 1/4 of the full load means current is full load divided by 4. Okay, that's what 1/4 means. So that means output power, voltage remains same, power factor is already given as 0.8. Okay, so those two remain same, only the current is going to be varied. So that means 1/4 full load means total rated kVA divided by 4 into the power factor. Okay, so total kVA is, 10 kVA is nothing but 10,000 volt amperes into power factor is 0.8, and 1/4 is coming because we are calculating output at 1/4 full load. So it will be 8K divided by 4, it will be equal to 2000 watts. Right. Is it clear? Output power at 1/4 full load.
Yes, sir.
Okay. So now you know ohmic loss at 1/4 full load, core losses at 1/4 full load, and output power at 1/4 full load. So all data is available. I think you can calculate the efficiency. So try to calculate efficiency at 1/4 full load, that efficiency value. One minus losses divided by input.
So 0.973.
Okay, so something like 0.973. So 97.3% is efficiency. Did any other person got that answer or something different from this?
Yes, sir. Same.
0.973.
Yes, sir.
Okay, so let's see that. So efficiency at 1/4 full load is 1 minus losses divided by input, 1 minus losses divided by output plus losses. Okay, right. So 1 minus core losses are 50, copper losses at 1/4 full load is 5 watts divided by this one. Okay, so you will get approximately 97.32%. Okay, so this is the efficiency at 1/4 of full load for the transformer given to you. Okay, so now in the question it was asked to find out efficiency at half of full load and at full load also for the same power factor. So try to calculate that at half of full load and at full load. Try to calculate efficiency. You have to find out the copper losses at half of full load and at full load, and also the output power at half of full load. Then you can calculate the efficiency. Try to do that.
So we have to find the efficiency.
Yeah, so what is the copper loss at half of full load that you say first? Copper loss at half of full load.
20.
20 watts.
20 watts.
20 watts. Okay. So what will be the output at half of full load?
4000 watts.
4000.
4000 watts. Okay. So now you calculate the efficiency.
98.28.
Percent.
Okay. So 98.28 or 98.3 approximately. Okay. Right. So others also have done it. All of you, please try to do that. Right. So efficiency at half of full load means only the variation will be in copper losses and the output power. Okay. Right. So copper losses will be 1/2 whole square because we are calculating at half of full load. 1/2 whole square into PSC, and output power will be 1/2 into rated voltage, rated output power at the given power factor. Okay. Okay. So this is the formula you have to use, and core losses remain same. Okay. So 1 minus 50 plus this will become 20 divided by, I think this will be 4000 plus 50 plus 20. Okay. So you'll get approximately 98.28%. Okay. Right. So this is the efficiency at half of full load. So quickly try to calculate what will be the efficiency at full load also.
Sir, 98.40.
98.40. Right. So 1 minus something like 50 plus 80.
Yes,
So it
sir.
will be 130 divided by 8000 plus 130. So something like that. Right. Right. So 1 minus 130 divided by 8130 maybe. Right. So if you do that, so you will get 98.4%. Okay, right. So that means your efficiency is going to vary with respect to load. That is occurring because your load is varying and your copper losses are also going to vary. Okay, right. So for the same power factor at different load currents, you are getting different efficiency values. Okay. I hope everyone is able to understand this. Okay. Only the copper losses will vary based on the load current, core losses remain same, and output power is also going to vary based on the load current because output voltage is approximately constant. Okay, we are assuming that. The second part of the question is calculate the load kVA output at which maximum efficiency occurs and also the value of maximum efficiency at 0.8 power factor. Okay, so they are asking us to calculate the kVA output at which maximum efficiency occurs. So how to find this? How to find that? kVA corresponding to maximum efficiency. We have already seen that. kVA corresponding to maximum efficiency is equals to N into rated kVA of the transformer. That N is given as root of core losses divided by full load copper losses. Okay, so find the value of N first. Okay, so once you know N, then you can find the value of kVA at which maximum efficiency occurs. Try to calculate what will be the value of N.
So can you show the question once again?
So
Okay, thank
part
you so
B
much.
is calculate the value of N at which maximum efficiency occurs for the transformer. What is the value of N here?
So for N, for the first part would be root 10.
No, we are value of N I am asking.
Sir,
N is
0.8.
N is some fraction I told, right?
Sir, 0.8.
Oh,
How you got that 0.8?
Sir, the root of 50 by 80. Means
Root of 50 by 80. Root
core
of
loss.
core loss by full load copper losses. Okay, so
Yes,
root
sir.
of 50 by 80, whatever value, that should be equals to the fraction N, which corresponds to maximum efficiency. Okay, so let the maximum efficiency occur at N times of the rated kVA. Okay. Okay, so the ohmic losses at maximum efficiency, we already know this, N square into 80. So first of all, we have to find out what is the value of N. Okay, so what maximum efficiency occurs when the ohmic losses and core losses are going to be equal. So N is given as root of core losses divided by full load copper loss. So 50 divided by 80, so that is something like 0.79 we are getting. Okay, so N will be 0.79. So kVA output at maximum efficiency will be N into rated kVA of the transformer, which is 10 kVA. So the kVA output at maximum efficiency is 7.9 kVA. Got it now? So everyone understood this, right? We have already discussed all these things. So N is nothing but root of core losses divided by full load copper loss. So from that you have to calculate N, and kVA corresponding to maximum efficiency is N into rated kVA, which is 7.9 kVA. Okay. Understood?
Yes, sir.
Okay. So now the other part is, for the question is calculate the maximum efficiency. That means they are asking us to calculate the efficiency at this point. Okay, so now we have calculated kVA corresponding to maximum efficiency and also the value of maximum efficiency at 0.8 power factor. So that means they are asking us to calculate the maximum efficiency value. So try to do that. You understood now what they are asking? At this output, they are asking us to calculate the efficiency. And the output kVA is 7.9 at 0.8 power factor. They are asking us again to calculate the efficiency. You can do it, right? You understood this or not? How what they're asking and how to proceed for that? Previously, I told like calculate the efficiency at 1/4 of the full load. Okay, that means 1/4 is 0.25. At half of full load, that means 0.5. Now we have seen the condition for maximum efficiency, which is 0.79. That means when your load current is equals to 0.79 into full load current, at that point you are going to get maximum efficiency. Okay, so now to calculate the maximum efficiency, previously it is 1/4, and another case it is 1/2. Now it is 0.79. You're understanding, right? So now the
Sir,
current is
maximum-
0.79 of your full load current. So at that point they are asking us to calculate the efficiency. You understood the question, na?
Yes, sir.
Okay. Okay, so please try to calculate the efficiency at this fraction. That means 0.79 full load current.
Sir, maximum efficiency is equal to 98.44%.
98.44%. Okay, what is the copper loss at this condition?
Sir, copper loss and both are 50, sir.
Both are 50. Okay. So what is the output power at this condition?
Out equal to 6320. This,
That
sir,
means
power factor
7.9 7900 into 0.8, right? Because output kVA is 7900 and you have to multiply with power factor to get the output power. So
Yes, sir.
right, so 0.79 into 10, okay, whatever it may be. Okay, right, so 0.79 into rated kVA into the power factor, which was given as 0.8, so that will be your output power. Okay, and losses will be 50, and this one will also become 50 only. If you calculate this one, 0.79 whole square into 80, it will be again equal to 50 only. Okay, right. So if you apply this formula, 1 minus losses divided by input at that condition, at maximum efficiency condition, you are going to get efficiency as 98.443. Okay, so that means the efficiency for the transformer will be maximum at 0.79 times of your full load current. Okay. Right. At that condition, you have got maximum efficiency as 98.44. Did everyone understood this or not?
Yes, sir.
Yes,
Right.
sir.
Okay. So this is how you have to calculate the efficiency. Core losses generally remain same, and copper losses should be calculated corresponding to the current. Okay. And output power also needs to be calculated corresponding to the current using the power factor data given. Okay. And then you have to use this formula to find out the efficiency at different loads. Okay. Right. So that's it regarding this efficiency related concept. Okay. So we have discussed regarding regulation and efficiency, and models of the problems will also be only this much. Okay. So no much models will be there because it's calculating efficiency, and efficiency at maximum load also we have already seen. Okay. So these are the only models. I think we have discussed some 4 models, I think so, in the complete transformer chapter. Okay. So with this, I think the transformer chapter is done. Okay. So there will not be any tutorial sheet regarding this chapter also, because only those 4 models will be there. So if you practice that, that is good enough. Okay. Right. So that's it for this chapter. So we'll start new chapter in the next class, maybe Monday. Okay. So induction motor will start on Monday. Okay. So that's it for today. So we'll meet back on Monday. Okay. So you can leave now. Yeah. So all can leave. Thank you. Thank you, all of you.
Thank you, sir.
Thank you, sir.
Yeah. Thank you. Thank you.
Thank you, sir.